The topic of today's lecture is optically active and optically inactive compounds. So, in this lecture, we'll be talking about compounds, chiral compounds, and achiral compounds, and we'll see which of them, show optical activity, and which of these compounds do not show optical activity. So let us start this lecture, and first of all, we'll see the link between optical activity and chirality. I think we have already talked about this, the concept of chirality in great detail in previous lectures. So in this lecture, we'll be focusing more on the precise topic of optical activity. Enantiomers, they are mirror image, non-superimposable mirror image isomers of each other. They are known as enantiomers, and chiral molecules, they show this enantiomerism. These enantiomers have many properties which are identical, like they have the same melting points, boiling points, and same solubilities. In fact, to be honest, that most of these, almost all of the physical properties of enantiomers are same. However, those properties which stem from how the different groups are arranged around this asymmetric carbon. If any properties depends on that arrangement, I think that particular property is going to be different for these two enantiomers, because these two enantiomers have different arrangement of atoms or groups around this asymmetric carbon. So these properties will be, they will not be identical. They will be dissimilar. We'll see those properties. What are those properties? And one of the properties that enantiomers that do not share is the way they interact with the plane polarized light. These enantiomers of a particular compound, like you have a compound uh, with one asymmetric carbon, means it will have two enantiomers. These two enantiomers will be identical to each other in almost every respect except their behavior towards plane polarized light. They will interact with this plane polarized light differently. So in this aspect, these enantiomers are different. First of all, we'll see what a plane polarized light is all about, which is also called as PPL in short. If we use a abbreviation, we'll use it as PPL. Normal light consists of electromagnetic waves that oscillate in all directions, that but plane polarized light, on the other hand, that it oscillates only in a single plane, passing through the path of propagation. So normal light has oscillations in all possible directions, while as plane polarized light has oscillation in a particular direction. So it's known as a plane polarized light. And this plane polarized light, PPL, is produced by passing normal light through a polarizer such as a Nicol prism. So how you get a PPL? You have to pass the normal light through some polarizer, for example Nicol prism. So this normal light is converted into a plane polarized light. This is how you get the plane polarized light. Here is the diagrammatic sketch of this plane polarized light. This is the light source here, you see, and here this is the normal light. It has oscillations in all possible directions, as mentioned here. Light waves oscillate in all directions. These are all directions are there. Okay, so this is the normal light. But when this light passes through a polarizer, when it passes through this polarizer, it can be a Nicol prism. This polarizer, it cuts out all the oscillations except one. So except one, all the other oscillations are cut out. So the emerging light from this Nicol prism, the emerging light, this light is known as the PPL. It's known as the plane polarized light. And here I have mentioned here that the light oscillates in a single plane only. So this is known as a plane polarized light. Okay, I hope it's clear. In 1985, this was all about plane polarized light. So this concept we are going to utilize in the next few slides. In 1815, Jean Baptiste Biot, who was a physicist actually, he discovered that some naturally occurring organic substances like camphor and the oil of turpentine or turpentine oil, they are able to rotate the plane of polarization of this PPL, plane polarized light. They have the capacity to rotate this plane of polarization. And he noted that some of the substances, they rotate this plane of polarization towards the right, towards clockwise, they rotate it, and some other substances, they rotate this plane counterclockwise. While as he also encountered some compounds, some substances which did not rotate the plane of polarization at all. So this is what he noted out. And then Van Hoff and Leibel, they later determined that the optical activity, this optical activity was it was associated with compounds having one or more asymmetric carbon. So this Van Hoff and Leibel, they demonstrated it, that the fact that compound rotates the plane of polarization clockwise or anti-clockwise or counterclockwise or anti-clockwise, it depends on the presence of one or more asymmetric carbons. Means if a compound has one or more asymmetric carbons, it will rotate the plane of polarization. If it doesn't have the one or more asymmetric carbons, it doesn't rotate the plane of polarization at all. So what are optically inactive compounds? We'll see the definition. So when this plane polarized light passes through a solution of an achiral molecule, you know now what are achiral molecules, which are not attached to four different groups or which has a plane of symmetry. We have discussed this in detail in previous lectures. So when this PPL passes through the solution of an achiral molecule, the light emerges from the solution with its plane of polarization unchanged. So the emerging light that comes from the solution of an achiral molecule, the plane of polarization of this light is unchanged, means it does not rotate the plane of polarization. So thus an achiral molecule, we can say an achiral molecule does not rotate the plane of polarization. This achiral molecule does not rotate the plane of polarization, and this molecule is said to be optically inactive. We call this molecule as optically inactive. A compound which does not rotate the plane of polarization either to clockwise or to anti-clockwise or to counterclockwise is known as an optically inactive substance or optically inactive compound. So example is here, this is the light source, this is the normal light here, this is a polarizer, this is the plane polarized light PPL, and in this tube we have an optically inactive compound. So the light here that comes out, the light here, emerging light from this solution, the plane of polarization has not been rotated. So we say that this substance here, in this, it is optically inactive substance because it has not rotated the plane of polarization of this PPL. So such molecules are known as optically inactive. On the other hand, optically active compounds, when plane polarized light passes through a solution of a chiral compound, what happens in that solution, the light emerges with its plane of polarization changed. So this light which comes from the solution of a chiral compound, the plane of polarization is changed, means it has rotated the plane of polarization. Thus a chiral compound rotates the plane of polarization and is said to be optically active. So optically active compound is a compound which rotates the plane of polarization either to clockwise or to counterclockwise. Okay, so an optically active compound rotates the plane of polarization to the right or to the left, to the clockwise or counterclockwise. And you have to note down here, if one enantiomer rotates the plane of polarization clockwise, its mirror image will rotate this ppl exactly the same amount counterclockwise. Suppose you have two enantiomers of a particular compound. If one rotates to the right, the other enantiomer will rotate the plane of polarization exactly the same amount to the left, right? So here is the representation of of a compound which is optically active. So this is the light source here, normal light source. This is this light has planes oscillations in all possible directions. This is a polarizer here. This is plane polarizer light. Okay, and this is the sample tube in which there is a chiral compound, right? And here you can see the plane of polarization of this light, it has changed. It has now changed there. It has the plane of polarization has been rotated to the right here. This plane of polarization has been rotated to the right. So such a compound is known as optically active compound. So chiral compounds are optically active, while as achiral compounds are optically inactive. Moving on, if an optically active compound rotates the plane of polarization clockwise, then we call it as a dextrorotatory enantiomer. It's known as the dextrorotatory stereoisomer. An optically active compound which rotates the plane of polarization to the right. It is indicated by plus sign in brackets or D sign, dextrorotatory. On the other hand, if an optically active compound rotates the plane of polarization counterclockwise, we call it as levorotatory, which is indicated by negative sign or L sign. So far it's clear. I hope it's very much clear so far. Here you have to note down some points which is very important. Do not confuse this positive sign and negative sign with R and S. They have nothing. This positive has nothing to do with R, or this positive has nothing to do with S, or this negative has nothing to do with R, or this negative has nothing to do with S. These positive and negative symbols indicate the direction. They simply indicate the direction in which an optically active compound rotates the plane of polarization. They only show the direction of rotation. If it is to the right, we show it. If it is to the clockwise, we show it by positive sign. If it is counterclockwise, we show it by negative sign. On the other hand, these R and S, notifications, these notations, they indicate the arrangement of groups about an asymmetric carbon. They simply show the configuration R and S. They have nothing to do with optical activity. Some compounds with R configuration can be positive or some can be negative. So there is no correlation. There is no link like some of you might have this concept that compounds with R configuration, they will rotate the plane of polarization to the right. No, this is absolutely wrong. There is no correlation. Or some of you might have this concept that compounds with S configuration, they rotate the plane of polarization to left and they are indicated by negative sign. No, it's wrong. There is no correlation between these terms. So an instrument which is called as the polarimeter is used to measure the degree to which an optically active compound rotates the plane of polarization. So such an instrument is known as polarimeter, and it calculates, it measures the degree to which an optically active compound rotates the plane of polarization. And this is a schematic diagram of a polarimeter. You have a source of light here, normal light, right? You have a polarizer here. This is the ppl, plane polarizer light. You have a compound here. This, you have a tube here, and this tube, sample tube, it contains, it can contain a chiral or an achiral compound. This is the plane polarizer light. This is the analyzer here, through which you can view it. Okay, there is some some marks are there. by which you can read by how much by how much degrees the light has been rotated. And this alpha here, this alpha is known as observed, it's called as the observed rotation. Observed rotation means how much it has been, the plane of polarization has been rotated. This is what you have to actually calculate, you have to measure. The sample to be measured is placed in the sample tube. So this is the sample tube here. The sample is placed in it. If the sample is optically active, it will rotate the plane of polarization. You know this. The difference between an optically inactive sample and the optically active sample is called observed rotation. So this difference between an optically active and inactive compound is, it's known as the observed rotation. And optically inactive sample will not rotate it, while as optically active it will rotate it. So the difference will be the observed rotation. So this difference is measured by rotating the analyzer on the polarimeter. The analyzer part on the polarimeter is rotated, so that we can measure the difference between the optical activity of an optically inactive sample and optically active sample. And this observed rotation alpha, it depends, it's measured in degrees and depends on many factors. Number one is the concentration of the sample, means the number of optically active molecules in the sample. Number two is the length of the sample tube, how lengthy this sample tube is. It also depends on temperature, and it also depends on the wavelength of the light. What kind of wavelength you are using, it also depends on that. So these are the factors which affect this observed rotation. So there is something called a specific rotation. Every molecule has a specific rotation. So each optically active compound has a characteristic specific rotation. So by definition, it is shown by this alpha square brackets. This is wavelength and this is temperature. So by definition, the specific rotation is the number of degrees of rotation caused by a solution of 1 gram of the compound per ml of the solution in a sample tube of 1 decimeter long at a specified temperature and wavelength. So this is known as specific rotation. So here you are specifying certain things, like specific rotation is the number of degrees of rotation caused by a solution of 1 gram. So you are defining here that the solution has to be 1 gram and the sample tube length has to be 1 decimeter and a particular temperature and at a particular wavelength. This is known as specific rotation, and every optically active compound has a characteristic specific rotation. And the specific rotation, it can be calculated from the observed rotation by using the following formula. So specific rotation is equal to alpha, this is observed rotation. L, alpha is the specific rotation, T is the temperature in degrees centigrade, lambda is the wavelength of the incident light, and alpha, this alpha here, this is the observed rotation that you analyze through the observer. L is the length of the sample tube in decimeters, and C is the concentration of the sample in grams per ml of solution. So if you know these alpha, L and C, you can easily calculate the specific rotation of a particular compound. And for example, 1 enantiomer of this 2-methyl-1-butanol, this compound, it has been found to have a specific rotation of plus 5.75, means it is the dextro. It's the dextro isomer. It means its mirror image rotates the plane of polarization to the same amount but in the opposite direction. It means that this enantiomer, which is the mirror image, these are mirror images of each other, right? They are mirror images. So its mirror image mirror image will have the same amount of specific rotation, but the direction will be opposed. So it is plus dextro is plus 5.75 and this is minus 5.75. So this is known as levo isomer. It's clear so far. I hope it's clear. You know, knowing whether a chiral molecule has the R or S configuration, it does not tell us anything, about the direction the compound rotates the plane of polarization. So R and S will tell you nothing. Suppose if you know whether a compound is R, so you cannot say whether it will rotate it plane of polarization to the right or left, because some compounds with the R configuration, they rotate the plane of polarization to the right, and some rotate the plane of polarization to the left. We have already discussed this point in previous slides in this very much lecture. So we can tell by looking at the structure of a compound whether it has R or S configuration. So by looking at the structure, you can only tell whether it is R or S. But the only way we can tell whether a compound is dextrorotatory or levorotatory is to put the compound in a polarimeter. So unless and until you put this compound in a polarimeter, you cannot know whether it is dextrorotatory or this is levorotatory. This is all for this lecture. In next lecture, we'll be talking about optical purity or enantiomeric excess. Till then, goodbye. Take care. Allah Hafiz.